much for the invitation and the opportunity to speak. It's a lovely location. It's also been a really great conference. I feel like I've learned a lot, so thanks to the organizers. Okay, so I was going to talk about Floer homology mostly, which you know is maybe not quite a typical subject here. But let's just start with the observation that topologist categorification is sort of the art of starting with a Tqft in dimensions 2 and 3 and extending it to Tqft in dimensions 2, 3, and 4. Now this program has been very successful sort of for relative TQFTs where we have, say, links inside of R3 and cobordisms between them, but less successful maybe for not relative TQFTs where we just have manifolds by themselves. And in fact, we have an existing example, really only, in my view, one interesting existing example of sort of 3-4 dimensional TQFTs coming from Floer homology. And so I want to talk about the kind of simplest version of those, which is HF hat. And so what does HF hat do? Well, to a closed oriented manifold Y, it assigns, let's say, HF hat of Y. This is a finite dimensional vector space over Z mod 2. This was constructed by Ojval and Szabo about 20 years ago. And okay, so it's supposed to be a TQFT, so I should have maps for cobordisms. And the first thing that you discover, or maybe the thing that you discover after some thought, is that cobordisms aren't just cobordisms between 3 manifolds, but between pointed 3 manifolds. This should give you some map from HF hat of Y naught, Z naught to HF hat of Y1, Z1. This is like the fundamental group in some sort of sense. It really depends on a base point. And this is a fact that actually Ojval and Szabo missed when they were first setting up the theory. It's really observed by Juhas, and then full functoriality was set up by Juhas, Thurston, and Zemke. Okay, and the key ingredient here really is the presence of sutures, which I'll explain in a little bit. Okay, and this kind of, the role of sutures in this theory was first discovered by Juhas. And that's what led him to this observation. Okay, now, so on the 2-3 side of this TQFT, we have an existing theory, which is so-called bordered Floer homology. Which is and Thurston, and its extension to bordered-sutured manifolds by Floer. And I guess the question I'm really interested in is understanding the extension of this to sort of 2, 3, 4. Okay, so, well, I feel like I know what you need to do to make this work, but there's still lots of things to check. Okay, so what should we have here? Well, we should have a 2-functor from some category, call it BS4 for bordered-sutured 4 manifolds, to cap. and that's the form that this HF hat should take. So the first thing I'd like to do is to kind of describe this category BS4. So BS stands for Bordered-Sutured manifolds. It's Zarev's name. And maybe let me first draw a picture. Okay, so Bordered-Sutured manifold is actually just the same kind of thing that Tudor was talking about in his talk yesterday. So on its boundary, it's got some part that's colored red and some part that's colored blue. And you could think of about these as being boundary conditions like Tudor had, and maybe this is colored by the bulk, in Tudor's words. Okay, so I guess what does that mean? It means that boundary of M is, let me say, B. That's this part that's colored by the bulk. It's bordered, union R plus and R minus. So collectively I'll call this R. Okay, maybe R plus is red and R minus is blue in this picture.
Sorry, this M is three-dimensional or two-dimensional?
So I'm flexible on the dimension of this M. This could be a statement in any dimension.
But in this example?
In this picture, it's three-dimensional. So it's got a, there's maybe a handle body here. On its boundary, I see this sutured disk. Okay, so this is the sutured part here. Okay, and maybe I'll kind of record this as a triple, where I have M, and then I know this set R, and I know R minus. Okay, if I know R minus, then I can take R plus by taking the complement. Okay, and the crucial condition here is that we always require M twiddle to be what we'll call well connected. In other words, every component of M, of boundary M, and of R intersects both R plus and R minus. Okay, so there's no such thing as three manifold with naked boundary with no suture on it. There's no such thing as a closed three manifold. You always have to have some suture on every piece of manifold that you're considering. Okay. So that's what I mean by a bordered-sutured manifold. And now we can talk about this category. So the category has objects. Okay, and the objects are sutured surfaces where the whole boundary is sutured. So there's no bordered part. So the whole boundary is sutured. And here I have, maybe I'll call this rho minus. Okay, so just to draw some pictures, right, so a perfectly good sutured surface might be, I take the disk, I put three blue sutures on it, and then the whole rest of the boundary is red. Or I could have a punctured torus where half of the boundary is a blue arc and the other half is a red arc. Or I could have maybe an annulus with two blue arcs here and so these are the objects.
So on all your examples, there is no B component in the boundary.
Yes, that's required for the, yes. Okay, so that's part of the requirement. You see here I wrote boundary sigma for what R was.
And I think that's the classical setting of sutures.
Yes.
All right.
Yeah, so, yeah, that's right. So,
But like sigma is a surface here.
yeah, sigma is a surface.
Okay, thank you.
And just to be sure,
This is what would be conventionally called just a sutured manifold.
just to be sure, it doesn't have to be connected.
No, it doesn't have to be connected. Yes, that's, I could take the union of a couple of these things if I wanted. Okay. Also notice that the empty set is a perfectly good object. It's a perfectly good bordered sutured manifold because it has no components, so you can get away with having no R minus. So then we have one morphisms. So that's a bordered sutured manifold. I dropped the requirement that it's totally sutured. So from sigma naught twiddle to sigma 1 twiddle. Here, forgot the thing that I wanted to say here. So if I have a manifold like this, I could look at the bordered boundary. So what is that? That's this set B, and then I'll write this as B intersect R, and this is B intersect R minus, but this actually would be the whole boundary of B if you think about it. Okay? So in particular, if I take the double boundary of my bordered sutured manifold, I get the empty set. Okay, so another way I could have said this is that boundary B of sigma is empty. Okay. All right, so one morphisms are like this, and here I want the boundary B of M twiddle to be minus sigma naught twiddle disjoint union sigma 1 twiddle. I should say that everything is oriented in this picture, all manifolds are oriented. Right, so again, for a picture, maybe you could think I've got something like this, where color this stuff in the back of the surface blue, and this region red. Okay, and then if I wanted to compose, maybe I could compose with this one morphism here, where this is colored blue. And I would just compose by gluing these together. Okay. And notice I should, right, so it's a little bit hard to draw these things in perspective. Maybe let me emphasize that, right, the boundary here, this manifold is the union of two disks on one side, and one disk on this side, and they've got so many sutures on each piece. Okay. So then,
Sorry, can you explain again? So this red and blue stuff is inside M? Or
the red and blue stuff is on the boundary of M.
so M is like...
M is this, in this case, M is this three manifold. They're all, both of the things I drew are homeomorphic to the three ball.
So this is like the field pair of ends on the
Yes,
left?
that's right.
And the boundary is like three white discs and the...
And the sutured region. So B would be the white disks, R plus would be red, and R minus would be blue. And then we can do the same thing for two morphisms. W twiddle. That's again going to be a bordered-sutured four-manifold now. Maybe, let's say, not twiddle, one twiddle, and here let's assume that n lot goes from sigma twiddle. One twiddle, and one goes from sigma lot twiddle to sigma one twiddle. And we have the usual picture, right? So you should think that here I've got and one and naught, and here I've got sigma naught times I, sigma 1 times I. Put some minus signs in here. And this is a picture of the bordered boundary of W twiddle. Okay, so there'll also be some sutured boundary that you should think of as just kind of living on the inside here. That's not part of this boundary. Okay, and then I compose horizontally and vertically in the obvious ways, and that's what the two categories looks like. So for example, there's a two-morphism from the empty set in this category to, well, I don't have S3. S3 is not an object in this category. But instead what I have is maybe S3 minus a little free ball, where the boundary of this three ball is colored red and blue. And so here I kind of have the morphism here would look like I take my finger and poke it into B4, so I get actually a little 3-disk here that's colored half red and half blue. And on its boundary, you see this sphere colored half red and half blue. Okay. So now, let's talk about how the functor should look. And so maybe it's easier to think about the kind of decategorified version of this functor first. So that usually goes by, it's a sort of variant of what's called Donaldson's Tqft. So this is the decategorification. And over here we'll write HF hat for the categorification. Okay, and so let's discuss what this does on objects. Okay, so an object, remember, is sigma twiddle, which is sigma, boundary sigma, and this rho minus. And here I'm just supposed to get associated to this group. And the group that I get is the exterior algebra on H1 of sigma relative to rho minus. And maybe it's worth noting that the well-connected hypothesis tells me that if I look at all of H star of sigma relative to rho minus, actually that's just supported in degree 1. Okay. That's what the well-connected hypothesis is doing for me. All right, what do I have over here? Is this categorification? Well, here I'm going to write down an object that's going to look awfully similar to what Christian was talking about. So I'll take, let me write it as the sum is k equals 0 to infinity of fk of sigma twiddle, where fk sigma twiddle is the Fukaya category of sim G of sigma. And so this is kind of manifold with boundary. And actually, one thing you should understand about Fukaya categories is that the theory is often easier for manifolds with boundary than manifolds without. Okay, so here I have to do what's called inserting a stop. I'm going to call this S plus K. This is the stop. So it's a subset of the boundary. And so S plus K is sort of everything that touches rho plus. It's an unfortunate feature of the notation that here, homology relative to this is rho minus, and over here, the conventional notation is to put the stop over here. Okay, but so here I have, what is this? Well, a point in sim G as sigma is, maybe let's call it Z, is a K tuple, oops, not G, too used to Haggard Floer homology, Z1 up through K, once in here. And I'll stop this anywhere where Z intersects rho plus, so anywhere it hits the red part. Okay. So maybe, you might wonder, what is well, over here I have the exterior algebra. Here I have the symmetric algebra. What's going on? Well, if I look at sort of the symmetric algebra on H1 of sigma, H star of sigma rho minus, well, this is supported purely in H1. So this naturally just gives me the exterior algebra. Okay. And again, this is, if you were to work in the closed case, this would be much worse. Okay, so important thing to understand is that part of the reason that this HF hat is easy is because this is homogeneous. Makes this Fukaya category something we can really compute and work with.
I'm sorry, I didn't understand your comment about taking the symmetric algebra of.
Well, so this, you should think of this as being like a a Z mod 2 graded thing. Yes, that's what. Yeah, sorry.
Okay.
So in the closed case, you would have H2 of sigma.
Yeah, absolutely, and it's zero, and it will be everything will be a lot harder. Yeah.
Excuse me. So this Fukaya category is understood combinatorially with generators and...
Yeah, so I'll talk about that.
Yes.
But over Z's are different.
Over.
Z, so clearly working with Z2, there is no difference between exterior and symmetric.
No, sorry, this is like, right, so this is the,
It's not a coefficient, it's a subject.
yeah, we should work with Z, this is like, maybe this is a super vector space is what I should call it. I think that works.
What objects are Z's again? The Z1s up to ZK?
Yeah, so those are points in sim K as sigma. Right, so a point in sim K as sigma is an unordered K tuple of points. Okay, so now let's maybe address Christian's question, talk a little bit more about how we might understand this thing. So we have a basis. No, that's not what I want to say. If I have kind of, let me say, a perfect handle decomposition of sigma relative to rho minus. Okay. So what do I mean by that? And I mean essentially just the thing that Christian was doing. So I take rho minus here, thicken it up. So I have rho minus times I. Okay, and then I want to add handles. Okay, and essentially I only allow myself to add one handles in this picture. That's kind of the perfect statement. Okay, so if I have a perfect handle decomposition, this gives me a basis of H1 or sigma relative to rho minus, and that basis is evident in this picture. Maybe I should use a color other than red or blue. So here's the basis element corresponding to this handle. Okay. And then obviously from that I get a basis of the exterior algebra. Okay, and what does that translate to over here? Okay, so having a basis here, the corresponding statement here is that we have generators of, let's say, F1 of sigma, so the Fukai category of just sigma itself. And then similarly here we get generators of K is sigma. Okay, and this is really, in some sense, the content of the bordered Floer homology. Okay, it's telling you not just these generators, okay, but what is this category? Maybe I'll just move over to this Floer now. So maybe let's just talk a little bit about F1 of sigma. Okay, so F1 of sigma, the objects are, let's say, twisted chain complexes. Okay, you could interpret that as saying that, you know, there's an operator D, but no homological grading. Over an algebra, say A of sigma, and maybe I'll write H here for this handle decomposition. So this algebra is the algebra that Lipschitz, Ushvath, and Thurston write down. Okay. And right, so the kind of idempotence in this algebra, which you should think about, it's like, you know, the objects that show up in your chain complex correspond to these generators. Okay, and then the morphisms between them are algebra elements. Okay, but actually in this one-dimensional situation, there's a remarkable structure theorem in this setting to Haydn, Tsarkov, Savich. And you know, we have to consider these chain complexes up to some suitable homotopy. Okay, but actually this category can be realized that indecomposable objects in this category correspond to sort of immersed curves on the surface with endpoints in rho minus. Okay, so a whole bunch of objects typically. And if they're closed, so you know, these things can have boundary, they can be arcs, but they're not required to. Closed curves can carry local systems. I mean, the arcs could carry local systems too, but those local systems are necessarily trivial, so not so interesting. Okay, so maybe one good thing to understand here is that in this one-dimensional case, we have a basis-independent understanding of this category. And in fact, right, so one of the, you know...
This is graded story. Is this graded story?
Graded,
You have grading on this
Right, so, yes, right.
These are graded objects?
There's a Z-mod 2 grading, which you could essentially obtain by orienting the arcs, but you could also carry around a Z grading if you're careful and the circumstances are right? Like,
Is algebra A is just an algebra or is it a DG algebra?
this is just an algebra. We'll get to the DG algebra in a second.
Okay, and this algebra is just the gentle algebra that people.
Yes, that's right. This algebra is what's called a gentle algebra. Okay. Right, so the comment I was going to make is why didn't Lipschitz, Oshroff, and Thurston just establish two functoriality as well, along with the kind of other things they did? And I think, a large part of the reason is that it's actually quite hard working in this kind of basis-dependent language to set things up in an invariant way, okay, that makes everything, right, like, there are lots of things where it's more convenient to think about vector spaces rather than vector spaces with a preferred basis. On the other hand, if you want to compute, you want to take that basis and compute with that basis, right? But for theoretical purposes, it's often better to think basis independent. Okay, so how about this FK as sigma? Okay, so now the objects are twisted complexes over, as Emmanuel was saying, a DGA. Okay, where again the idempotence corresponds to sort of generators for wedge K of H1. And maybe this is a good point to note. So I wrote down this infinite sum here. Okay, but actually, this wedge product is finite. Okay, unlike in Christian's case, this sum is also finite as well. Okay, so once this has no objects, if K is bigger than the first Betti number of sigma relative to rho minus. Okay, so this is really finite. So, and again, Lipschitz, Oshroff, and Thurston wrote down an explicit recipe for how you get this DGA and how you calculate with it. We've got no analog of this structure theorem anymore. Okay, so that's an unfortunate fact, but and so the remark that I wanted to make, though, okay, is that just as we get from H1, there's a well-defined operation that takes us from V to its exterior algebra. Okay, so simply to set up functoriality here, what you want to do is you want to say there's a well-defined operation that takes us from this general algebra to here, that sort of Morita equivalent. General algebras give you equivalent things down here. Okay. And, maybe just, maybe it would be good to have an example at this point. Okay, so just to show that, they're interesting, non-trivial examples. Say I take S3 minus the complement of the trefoil knot. Okay. So that's a manifold with torus boundary. So I need to suture the boundary a little bit. Put a little suture disk on it like this. And then I could ask, I haven't talked about one morphisms yet, but I should get, this is a one morphism from the empty set to the 2 torus, this little suture disk, and R minus, which is the blue part. Okay, corresponding to that, well, this is just vector spaces. I take the, the one-dimensional vector space. Here I should get an object in, let's call it HF hat of M actually in this case it lives in Foup 1 of this is sigma twiddle. Okay. So that's, that's some actual, by the structure theorem, that's some actual curve in this punctured torus. And let me just draw the curve for you. I'm actually going to draw a lift of the punctured torus. Okay, this lift is the one in which the curve that remains closed is the longitude of the knot. And then I should have made this yellow. Okay, so this is the actual curve that we get. Okay. So one of the things that's good about this theory is we can actually compute, at least in this torus boundary case, a whole lot of things. Okay, so we know what this curve looks like for a lot of 3D movements. Okay, so now let me try and talk a little bit about one morphisms. And the thing that I want to say is that we can set this theory up in a way that's similar to, the kind of general categorification scheme that works well for knots and links. Okay, so I can give kind of a generator's description of what these morphisms are. Okay, and then we can hope to check relations to see that we actually get an invariant. Okay. And maybe let me first comment a bit on grading. Okay, so it's more natural to shift the grading to be symmetric. So remember, this vanishes when k is bigger than the first Betti number. So by minus 1/2, the first Betti number. Okay, and that'll make this S star a symmetric thing. Okay. And then their grading shifts corresponding to one morphism given by, so a morphism shifts the grading, this renormalized grading, by the Euler characteristic of R plus minus the Euler characteristic of R minus over 2. This is a nice grading here. Okay. And, well, so generators for one morphisms correspond to, let me say, Morse moves in a bolt in R and in, let's say, boundary of R minus. Let me sort of draw a few pictures to illustrate what's going on in each of these cases. So, in the bolt, just three-dimensional Morse moves. So I could add a 0 handle. I could go to the empty set. This is a B3, but that's not allowed because this doesn't have any sutures on its boundary, and that's not a valid morphism. So in fact, I have to sort of insert a little sutured disk here. This. And then if you think about, maybe let me just talk about the kind of the decategorified version here. So if you think about what is the decategorified version, well, that's actually a map from lambda star of the zero vector space to lambda star of the zero vector space. Okay, because here I'm taking h1 of this disk relative to an arc and its boundary, and that's 0. And of course that categorifies to, I don't know what, the identity morphism from. So this is an extremely boring cobordism. An interesting cobordism is, say, one-handle addition. Okay, so where maybe I take a piece of my surface that looks like this, and then I add a one-handle. Okay, and when I add the one-handle, I get a distinguished curve here, which is the compressing disk for the one-handle. That's not a suture or anything like that. And we'll just imagine that there are some sutures kind of away from this picture. Okay, so here, if I work out what this map is, it turns out that it's a map from wedge star of, let's call it h1 of sigma naught rho naught minus to wedge star plus 1 of h1 of sigma 1 rho 1 minus. Okay. And so this map is given in the following way. I take an element x, I'm going to raise the grading by 1. I'm going to write this as I'm going to do pi 1 inverse, let's say pi naught inverse pi 1 of x wedge alpha. Okay. Where here I've got, if I sort of took away the handle that I added, and the disk that I added down here, I'd have an open surface with maps to sigma naught and sigma 1. This is pi naught and pi 1. Okay, this choice of pi naught inverse is not well defined. By itself, this expression is not a well-defined thing, but the sort of variability in the choice exactly works out to alpha. So when I wedge, I get something that's well-defined. All right. Okay, and again, these are, this is the thing that Donaldson wrote down originally.
So sigma upstairs 0. It's a cobordism. It's a 3-dimensional.
So the way I've written it is that there's a surface that both sigma 0 and sigma 1 share in common.
The intersection of that.
But you could probably express this in terms of correspondence.
So for 3 manifolds, do you see some kind of spin structure on the 3 manifold?
Okay. I'll talk about spin C structure. Yes, so you can say precisely how the spin C structures work. I'll talk about that hopefully towards the end, which is fast approaching. Okay, so similarly for a two-handle addition, I'm not going to try and draw a picture, but basically I attach a two-handle along a curve beta, then this becomes, I get a contraction. So x goes to, here I take x, I contract it with beta, and then I take sort of, again, pi 0 inverse pi 1. Okay, you can see that sort of dual to this operation. And again, you know, it's exactly this contraction that makes this map well defined. Okay, and then there's, maybe I won't write, similarly there's a three-handle addition, but the three-handle addition, you again have to add a three-handle with a bit of suture on it, and you again get a map that looks exactly like that top one. So that's pretty boring. Okay. I think. All right, so then we have, for example, worst moves in R. And I think actually these are, you know, it's interesting to understand these. So for example, there's a Morse move in R that as a picture just corresponds to having a little sutured region appear. Okay, and as a cobordism, what does that look like? It looks like I've got this. Take this surface, cross it with the interval, but then I kind of poke my finger down and my finger's got some red and blue ink on it. So I have a little depressed disc here where it's red and blue. Okay. And again, there's a distinguished circle alpha here. And the map that I see is something like x goes to, I'm going to say pi 1 inverse pi naught. Oops, pi 1 pi naught inverse of x, wedge this alpha. Okay, so I pick up the factor of alpha here. And actually, you could have seen that from what I wrote down already. Because another way to create this is to start with my surface like this, add a zero handle, which has to have a little sutured region on it. Okay, and then add a one handle. Kind of have like this eye coming out or something. That's the same cobordism. And the compressing disk for the one handle here is exactly that circle that we had here. Okay, so that's maybe a little easy. So a more interesting example is where I increase the size of R plus. I have a cobordism that looks like this. And then the sutured region gets bigger. And now the sutured region maybe becomes something like this. Okay. And again, there's a distinguished beta here. And this map is, I'm just going to say this is given by contract with beta. To actually do this theory, we have to, give the categorified description of all of these things. And one.
I'm confused. On the left, this should be sort of two red stripes.
Yeah, it should be two, yeah.
There should be two red stripes.
Or is it sort of all to the left, the whole?
So this is, yeah. So this thing here is a region in the boundary of my surface. And I see a region of the boundary of my surface that happens to bump into two parts of the red sutured region. Okay, and then the red sutured region gets bigger over here, and now I've got.
Yeah, you can remove then the two outer vertical lines from the second picture, or add it to the.
Yes.
Okay, I see. Yes, I should erase the two outer vertical.
Yeah, okay.
Sorry.
Okay.
Thank you. Yes, much better.
Yeah. Okay.
Okay. And on the other hand, I could do the same picture, but with beta. So I could take this and map it to this where I've added this in. Okay. And here the map, actually, here the degree stays the same, and the map is basically an excision map. So here I'm looking at kind of, let's say, H1 as sigma naught, R minus naught, to H1 of, well, this is isomorphic to H1 of sigma naught, let's just, relative to R minus, this has a map to H1 of sigma 1 relative to R minus. Sigma 1's this thing over here, and again by excision this is isomorphic to H1 of sigma 1 relative to R minus 1. I guess this is R minus 1. Okay, so this, maybe it's easier for me to say what this map does if I just draw a picture. I have this arc, I just cut it. You see, this gives me kind of a well-defined homology class here. Okay. All right, so I think I'm almost out of time. There are also some maps in sort of Morse moves in R minus. So for example, I could take a bit of my surface that, how should I do this? Let me just draw it this way. So maybe I've got a bit of blue surface and then it suddenly grows a bit of red surface inside of it. There are 4 maps like this. I'm not going to write them all down. Actually, you can derive all of these from these one-handle addition maps and the two-handle addition maps. So there are 2 of them that are basically given by inclusions and 2 of them that are given by, well, one by wedge and one by contraction. Okay. So then, what I'd like to say in the remaining time is that, of course, I should also tell you how to compute 2 morphisms. So let me just comment that 2 morphisms are pretty much determined by duality in an appropriate sense. So in the sense maybe that if I have this 2 morphism here, M naught, M1, and W, well, I could think about that as being a cobordism with sort of just an ordinary 3-dimensional cobordism here with M1 and M naught glued together along their boundary. Okay, and then I can, this morphism here is a Hom. On the other hand, this thing maps into the Hom between these 2 things. So maybe that's all I'll say about that. And then the last thing that I wanted to do is maybe to sort of address Eugene's question a little bit and also come back to what Christian was doing. So just thinking about the decategorified version of the theory. All right, so, and maybe let's just assume that we have one morphism from the empty set, M twiddle. Okay, so then we get HF hat of M twiddle. Its decategorification is just its homology class in the symmetric product. The homology group is isomorphic to some lambda k of H1. Okay, and actually this decategorification is a really boring theory. Okay, what does it do? Well, I could look at the inclusion mapping from H1 of, say, sigma, so boundary B of M twiddle, sigma twiddle, relative to rho minus to H1 of M relative to R minus. Okay, and so actually this homology class is none other than the size of the co-kernel of I multiplied by lambda top of the kernel of I. And if this co-kernel of I is infinite, then this number is 0. Okay? But I get something more interesting. In fact, the whole theory works with twisted coefficients. Okay. So now let me say the following. So I have this map, let's call it J, from H1 of K of sigma to H1 of sigma to H1 of M. And I take let's call it sim k twiddle to be the covering space corresponding to the kernel of J. Okay, so in the case of the trefoil complement, that's actually the picture that I drew before. That covering space looks like that infinite loop. It's got punctures like this. And so then actually the claim is that there's a lifted invariant with twisted coefficients, which is in this covering space. Okay, and now the decategorification is a little more interesting. This is actually basically equivalent to the Alexander polynomial of k if k if m is a Mach complement. Okay, and you can see that right here. And so I'm supposed to take the homology class of this curve. What does the homology class of this curve have to do with the Alexander polynomial of the trefoil? Well, I look at the intersections with these vertical lines, and I see t inverse minus 1 and t here. Yeah. And so, for example, okay, so finally to answer Eugene's question, and then I'll stop. Right, so really I should have said that, actually I get one of these for each spin C structure, and the spin C structures are just in bijection with this co-kernel of I that we had before. For example, the fact that the Alexander polynomial evaluates to 1 is the fact that if I take each of these spin C structures and look at its image back down in the original uncovered thing, this is just one copy of lambda top. Okay, so here, and now I'll stop.
Thank you. So, are there questions or remarks? Yes.
We've seen Christian's talk where he constructed this representation of the mapping class group. Is it just possible just to use what he said, compute one of some?
Yeah, no, that's a great question. I mean, probably you could ask Christian and Anna. But yeah, let me say that one of my purposes in talking about this is I think that I think it's interesting to ask: are there other functors from this category BS4 or from BS3, the sort of 2-3 part of it, to, maybe you could first ask, are there functors from the 2-3 part just vectors, vector spaces and linear maps, right? Because somehow, we have tons of 3-dimensional TQFTs or 2-dimensional TQFTs, but not many 4-dimensional TQFTs that look interesting. Right? So maybe, maybe it would be easier to find some of them that look like this HF hat, which isn't, if you were to look for HF hat just, in the ordinary category, you wouldn't find it, because it's not defined on that category. So I'd like to advertise the idea that, maybe we should look for other.
Can this be fully extended to dimension 0, or it's not?
So that's a great question. Even dimension 1, I'm not sure, not so sure about. Like in dimension 1, there's a natural thing you can do, right? Which is there's this kind of Ganatra-Pardon-Shendy theory of Liouville sectors and kind of breaking one of these. The symmetric product is a Liouville manifold. Breaking it up into Liouville sectors and computing kind of piecewise on those, right? That's really what this Ganatra-Pardon-Shendy thing does. So it seems plausible that you could use that to go down to 1. But I haven't thought about it enough to really know whether that would have a chance of working or not. Again, like one of the things, you'll have to decide what the geometric category is first, right? Like there should be, right? Because now it's a little bit weird, right? These sutures, you're going to kind of run out of room to suture things, so you have to think about what happens. But yeah, there's a natural question.
So this procedure, when you go from F1 to FK, you need like a couple more words.
Sorry, say it again?
So you say that Fukaya-Kaiser group for symmetric powers is kind of determined by the Fukaya-Kaiser group of the surface?
Yeah. So that's if, right, it's kind of if you think about the kind of LOT algebras, how they're determined, the one, yeah, okay, maybe we could talk about it after, but, basically there's a kind of one-strand version of the LOT algebra, and, the thing for the K thing has K strands instead, and you want to kind of imitate that construction on the morphisms.
Right, but then you have some differential, which is kind of determined by some higher structure on degree 1, or?
So the differential, so the differential again comes from thinking about sort of resolving intersections between these multiple strands, right? And of course, the reason there's no differential in the K equals 1 case is that there's only one strand. So you do kind of the same thing with a differential, is what I would say.
Let's go.
Questions? So let's thank the speaker again and have tea.